So I'm going to teach like this. And I will post the recording afterwards so people who want to watch afterwards can. Maybe more people will come in as we go along. Anyways, I made a PDF file or made an RMD as I usually do, and this RMD covers the topics of linear regression. Now you might not be totally clear on the ideas, and that's fine. If at any point you feel like if I ask a question, it seems a bit poignant and you don't know how to ask the question, that's fine too. I'll just kind of fill in the space. But if you do have a question that you feel might occur in your assignment, feel free to ask me. So this is actually an example that Ken has in his notes. He doesn't have the answers for it, but he has as an example. It's actually rainfall data in California. So obviously they want to understand whether or not they can predict rainfall each year from certain measurements. Of course, you can imagine that maybe that's kind of important because it'd be nice to know, if you can kind of predict bad weather before it actually occurs, you might, adjust for it, compensate for it when you go outside that particular day, or you might choose not to leave your helmet off, it's going to rain that day, or if you have a suspicion it will rain. This is actually from 30 different weather stations in California, because it's kind of a very big state. And they're trying to see what are the things that might influence rainfall. This is kind of funny because you can imagine that if they're going to, the model includes things like, I'll just show you the data set. The model includes things like latitude and longitude. So if I just do view of rain data, you'll see that it includes things like latitude, altitude, which are things that are spatial. So you might think that one reason why this model is a bit weak is because you might imagine that, if you're going to include things that are spatial, you might not want to include them as a fixed fact. You might want them to be random, and really this might actually be better equipped with a spatial model, but we're going to assume that it's right now it's not a spatial model. We're going to assume that it's just a linear model and use the things we have to predict rainfall in California. But like I said, if you're going to use things that are geographical or things that are almost spatial, you might think to use kind of spatial map, but that's beyond the scope of the course. We're going to do linear regression here. Yeah, so I'm going to use read table here. That's because read table 2. Read table is a bit more rigid in the sense that it requires only one space between each column, and it has to have the position of the entries within each thing has to be the same, right? So you have to have the position of each entry in your column has to be the same, and there has to be exactly one space between them. But I think that if you look at the data set that Ken gave you, it's actually not quite true. It doesn't follow this pattern here. So read _ table 2 is a bit more flexible. And you should check these things. So if you look at the initial data set that you work with, you might see that it doesn't look like what you could use a read _ table for. There's only one delimiter that separates them. I think it actually has more than one. So you can see there's actually 2 spaces here. So there's something weird here. There's more than one space here. Then all of a sudden there's a space here. So while there's a space between these things here, there's more than one over here. So if you use read _ table, it will not make sense of what's going on here. Read _ 2 is more flexible because it kind of recognizes this, and then you get something that makes more sense. You get something that looks like this. Whereas you will get something different if you use read _ table. Okay. That's just something to figure out, because when your final exam, if you have to do something where if it knock on wood, it's actually online and you don't know why you can't read in your data, you might want to check those things. Anyways, the first thing that his thing says, it says make a box plot, rainfall figures, and explain why the values are reasonable. I think I'm actually marking this assignment, to be honest. So if you at all feel confused about what your answer is going to be, make sure you ask me. So I'm going to give an answer that I think is reasonable. Then think about your own answer for your assignment. So here it says make a box plot for rainfall figures and explain why the values are reasonable. Here he makes a note that rainfall can't be negative, which is something you should know. So if you get data sets where the actual lower bound doesn't make sense, it's probably a mistake or an outlier. So if you haven't, you would notice you have unusual points if you're talking about time or distance, yet you have negative values. So check for those things. Big outliers are obvious, but even small things where you have negative values are things you might want to check as well that you might want to remove, right? So this is why it's reasonable. when I make a block plot of the thing, you can see that certainly it's the case that for the most part, you have no values that are below 0. You do have a couple of outliers in certain regions, but it doesn't really exceed around, like, let's say 65 inches, right? So you can check and see as well. If you just attach the data frame, you can see that for the most part, these are the kind of things he asks when he does it. He does say, does your data make sense? You will see that you should check these, you should check the summary. Anyways, it does make sense because you have no negative values and the values don't get too big, because rainfall doesn't usually get that big. Maybe it's summarized actually. No, it should be summary. Summary of rainfall. Yeah, there you go. So you can see that the maximum is at 75, which isn't that big. Anyways, I really want to get to the actual LM model because you're going to be doing, this is the first week you do LM, I think, in your assignments. He says plot rainfall against other quantitative variables. It is not station. First of all, I want to point out, if you look at the station, if you look at the variable for, there's one that is actually not continuous. That's this one here. And while you can put a variable that's discrete into the linear regression model, the reason why he doesn't ask you to plot the relationship of X versus Y is because you cannot actually see how X is moving with Y when your variable is discrete, because it doesn't look like a positive. You don't see a linear line of one particular value increasing as the other increases, because you don't have a continuous thing. So this is why he asked you to make a line of best fit for these 3 continuous variables that are predictive variables, and you'll see that one emerges as a leader in your model. So I actually did a couple of things. If you're asked to plot more than one predictive variable, I put a function called grid extra. You may want to actually install that. I think it's just install that package as grid extra. It's in CRAN. The reason why is because you will see that when I do this, I guess when it looks like this, I wanted to create a sort of like a plot that puts the things in the same panel. Grid arrange does that. So that's why I used it. So you could obviously use facet as well, but the reason why I don't use facet here is because I'm not faceting based on a categorical variable that is binary or whatnot, like I did last week with the gender thing. And I looked at the mortality of male versus females. That's not a thing here. I don't have a discrete variable that I'm faceting on. So I can't actually use facet in this thing. What I can do is put them on the same panel by using grid arrange, whereas I cannot use facet here. Anyways, you can see that the first variable, which is, I guess, altitude, is not that strongly predictive. Well, there is some kind of linear thing that's positive. It's not very strong. And in fact, most of the points don't even follow the line of best fit. This blue line you see here is actually a linear regression model that gave a line of best fit, where the points don't actually follow that line, which means that if you actually made a linear regression model based on just this particular variable, it probably wouldn't yield a very good predictive model. Rainfall is, to some extent, rainfall against latitude is pretty strongly positive. You can actually see that it's probably the best predictor you have. Most of the points are kind of close to the line, and as one increases, the other one increases as well. The other one is actually, the last one's actually from coast. That means like whether or not you're kind of on the coast of LA or not. You can actually see that there's a negative correlation, but it's not very strong either. It's not as good. So that you can see that really actually the one that's most predictive is latitude. You might find if you add the other 2 variables to the model, it's not actually very predictive. It probably won't give you what you think it's going to give you, right? So the most predictive one is actually latitude. He might actually give you in your assignment a situation where you actually have more than one variable. Then it's the choice up to you as which ones you include in your model, and you don't have to include them all, which means you have to have the wherewithal in some sense to realize that you can include some and not the others, right? So some coefficients won't be significant. And actually, this is the very first lab where you discuss the notion of statistical significance, right? So I'm going to fit a linear regression model. You're going to see that he's going to ask you to pull out a whole bunch of things in that model. Then he's going to ask you, is there a significant relationship? And this one, you have to recall back the things you learned in B57, where you looked at the null hypothesis and the p-value, maybe very briefly, and then use that to determine if your coefficient is significant. Now, the reason why you chose latitude here is because it's the variable that is most significant, right? So it doesn't make sense to do an LM model based on altitude or from coast alone when those were not very significant from the scatter plot. But what you can see here is that this is LM for linear model. If you look online for code and use GLM, it will work too, because I believe the GLM default is actually, sorry, it will work too, but you have to put family equals normal, I believe, right? Or sorry, Gaussian. But don't use it, obviously, right? Try not to use it. But the thing is, GLM is a generalized linear model. So if you go on to take other courses, you will see that GLM is generalized linear models. So when your link function is no longer, you don't have a linear model, and maybe you have logistic, you would use a GLM. But GLM Gaussian is the same thing as saying LM normal, because just linear model, because obviously linear model is coming from a Gaussian model where the family is like normal, right? So you guys know from BP7 that when your family is Gaussian, that's when you have the LM model. So you can see that whatever I get here as an estimate will kind of yield the same thing as what I got from here. It's the same model, right? It's doing the same thing. This is just, the only thing is you can only use LM for linear things. You cannot put logistic regression models into the LM function. What you can see here is a couple of things. First of all, you can actually see the estimates themselves. So there's a couple of things he wants you to know. He wants you to know the R squared value, the slope, the intercept, and then it's significant. So if I were to write this out, I can from the actual output, right? So first of all, these are fitted values, right? So if your model is actually the following, your model is actually yi is approximately normal, but the mean that is given to you is beta naught plus beta 1 xi. Oh, sorry, let me write this a bit better. Xi, and then variance is sigma squared, which means you can actually express this as the following, which you might have in his lecture notes, where the error terms themselves are normal with a mean of 0 and a variance of sigma squared. The problem is that you actually don't know what these two parameters, what you really want to find is beta naught and beta 1, because that's your intercepting slope. But the problem is you actually don't have a way, you cannot actually directly compute that because you don't have that, all you have is a sample. So you will get an estimator of that thing you want to find, which means that what your actual thing is doing in R, what R is actually doing is R is actually finding the following. R is finding, so that means that if you want to find the expected value of this thing. So the reason why this is a Gaussian model is because if your yi is distributed normal, that means your line of best fit, if this is xi and this is yi, what you're saying is that actually the value of y is conditional on x. So conditional on x, your value of y is changing. That's why you see that y is conditional on x. What you really actually have here is a line of best fit, and you have points around it that have a distribution as normal, right? So maybe one point is circled on the line here, but you can see that your distribution is normal and you get points along the line. And actually what it's saying is that the expected value of yi given xi is going to be equal to beta naught plus beta 1 xi, but you can actually find that. So when you take the expected value of this whole thing here, we take the expected value of this thing here, you get this, because obviously the mean of the error terms is 0. So when you take the expected value of this whole thing, this fades off into 0. But the problem is that you cannot actually compute this thing here because you don't know what beta naught and beta 1 is. What you have is estimators of this thing here. So what you actually really have is the following. You have yi hat, which is supposed to be an estimator of this, is equal to beta naught hat plus beta 1 hat xi, right? This means that what you get in the actual R output is actually an estimator of beta naught and beta 1. It's not actually beta naught and beta 1 itself. It is an estimator of those things, right? So this is what you're really looking at, is an estimator of those things. It's not actually beta naught and beta 1 itself, which means that in this example here, it turns out that beta naught is actually minus 13 or minus 113.3028 plus the slope term is actually 3.5950. So this line of best fit is actually y hat is equal to minus 113.3028 plus 3.5950 times latitude, as in like when the latitude is changing by unit increase in 1, the mean rainfall you get in California is given by a factor of whatever. So you can see it's a positive relationship where this is increasing, whereas when your latitude increases by like 1 degree, I guess, you will see that your estimated rainfall will increase by a factor of 3.59. Now you can see that this slope term is positive. That makes sense because when you look at the relationship latitude had, it's positive with rainfall basically. Yeah, so error is similar to residuals, except that the little twist here is that a residual, so an error term is the following. So an error term EI, so this is a residual. It's actually equal to yi hat minus yi, which is equal to beta naught hat minus beta 1 hat xi. Actually, I think it's the other way around. I think it's yi minus 6, I think it's this. It's yi minus yi hat. That's your residual basically. But your error term EI is actually equal to yi minus beta naught minus beta 1 xi. So what is this? This is actually yi minus beta naught hat minus beta 1 hat xi. So you can actually see that the residual is an estimator of the error basically. So the residual estimates the error basically. Residuals estimate the error, but they're not the same thing, because the thing is, you can't actually compute the error because you don't know what beta naught and beta 1 is. You can compute the residuals. So the residual is actually an estimator of the error, but you actually cannot compute the error itself. So that makes sense. That's why you actually see, that's why you see the form looks kind of similar. And that's why you in some sense felt compelled to say, is the residual the error? Because it looks kind of similar in their form, but it's not quite the same thing, right? So that's why you have that, right? So, yeah, so they're related, but not quite the same thing. So that's actually why when you look at the actual estimator for sigma squared, the estimator for sigma squared is actually equal to, you know, this estimator here for sigma squared is actually equal to sum of yi minus yi hat squared. It's like minus n minus, I guess, p minus 1, depending on your thing. You can see that it's related to your actual residuals because your residual is supposed to estimate your error, basically. Right? So they're related, but not quite the same thing. But good question. You can see the form is similar, but they're not quite the same thing. Yeah. So what to note from the thing here is you should note that your line of best fit is actually minus 113.3028 plus 3.950. The other thing to note is actually that he wanted you to find the R squared. Your actual R squared is this basically. You can see that it's 0.3326. That's not incredibly high. So what is R squared? R squared is actually equal to the correlation itself squared, right? So this means that, technically speaking, that implies that your correlation itself, take the square root of this R squared, you get your correlation. You might say, isn't it true that the roots can be positive or negative? Yes, but the reason why we take it to be positive in this instance here is because we can see that the relationship between latitude and rainfall is positive. So that means that the correlation here is positive. It's not actually negative. So it's actually the square root of this 0.33, I think 29, which isn't incredibly high. I mean, it's not that strong of a relationship, right? It means your correlation is probably not that high. What you actually have is this. It's like 0.5678. So your actual correlation between your latitude and rainfall is like this. But what is actually R squared? R squared is actually called the coefficient of determination. This is actually called the coefficient of determination. The reason why it's called the coefficient of determination is because you're trying to determine how much of the variation you see in the change in Y is attributed to its relationship with X, right? So if the relationship between X and Y is pretty high, you should see that as Y is increasing, then X is increasing in the same direction, and the relationship is pretty strong, right? So it tells you how much of the variation you see is attributed to what you see in X. Now, the fact that your R squared is only 0.3326 would probably indicate that your correlation is probably actually fairly weak. to some extent. Well, no, actually moderate. You can see that this is actually a moderate correlation. It's not that strong, it's moderate, right? Because, so this is actually a moderate correlation. What does that mean? Actually, it actually means that if you do 1 minus 0.3326, you'll see that actually almost 70% of the variation you see in your change in Y is actually not attributed to X. So it's something you're missing in your model that makes it so you cannot totally predict X. So you cannot totally predict Y from X. And it kind of makes sense too, because if I go back and I put, for example, if I put the, what do you call it? If I go back and I put this, the standard errors on the actual latitude, you'll see that it's actually not that good. The confidence bands are actually pretty wide, which indicates your model is where there's something missing, right? You don't, especially over here, where you have sparse data, you actually have pretty wide confidence bands, indicating there's something in your model, this in your model is missing, right? That in terms of attributing Y from X. So that's essentially why your R squared is low. Now notice that I pulled up this one here. I did not take the adjusted R squared. Please don't in your assignment, right? So when he asks you to find the R squared values, he's not referring to the adjusted R squared. The adjusted R squared is something you use for model selection. That is something different entirely, right? So you're actually using the multiple R squared in your output. The adjusted R squared is something else that is related to model selection. It is not itself the thing it is not R squared, right? So don't get confused and use the wrong thing in your, that's not right. It's not true that, it is not true that they're the same. And it's very easy to pull the wrong one. So you're looking at the multiple R squared, not the adjusted R squared, right? The other thing is you can notice that your p-value here is the same as the p-value you have here. The reason why these two p-values are the exact same is because you only really have one predictive variable. If you add more than one predictive variable to this model, your p-value here will not be the same as the p-value here, because you would have more than one slope term in this output. And so the p-value you see over here will be the combination of all the significant p-values over here, right? So the p-value you achieve here when you have more than one predictive variable would actually be a sort of average in some sense of all the p-values. You would also notice your F statistic would not be directly related to your t-test here, because you can see that over here, F is actually the square of this t statistic here, right? So if you square 3.736, you will get the F you see in the output. So let's just confirm that 3.726 squared. You see that it's the same F you get here. That would not be true if you have more than one predictive variable. So you can see that the F statistic you get here will be an average of all the F statistics you had for more than one predictive variable. And so the p-value would actually be an average of all those tests you had here. But you can see that your actual model, even though your R squared is not very high necessarily because you only have a moderate relationship, actually your coefficient is significant. You can see that this p-value is a lot less than 0.05. So if you're set up a formal test, if you set up a formal test here where you have, the null hypothesis, where you have beta 1 is equal to 0 versus the alternative, you're suggesting that it's not 0. You have a distribution on the null. The t statistic is doing the following. It's saying, okay, compare what you got in the sample to your predicted beta 1, which is obviously 0. What you're looking at basically is the t-test that looks at this, because obviously you're hypothesizing the null that it's 0. Now, if your null hypothesis is true, your t statistic will be close to 0, because obviously if your actual beta 1 hat is close to 0, and these two are close to 0, your t-test will be kind of over here. The extent to which your actual t statistic goes into the tails will tell you that it's kind of far from the null hypothesis of 0, right? Your t statistic is actually 3.736. So it's actually 3.7. You can actually confirm this as well, right? Just take the ratio of this estimate here, which is 3.5950, and divide it by your standard error here. So take this, you can divide it into this, because this standard error is actually S at beta 1 hat. If you divide these two things, you will actually get this. This is why this is the t-value. This is why this is the t-value for this test. It is literally the ratio of your estimate divided by your standard error. Your t-statistic is somewhere over here. Let's suppose this is like 3.736. So an observation is considered extreme if it's at this value here or more extreme. Right. So the question is, how extreme is this? Like, is this considered far enough into the tail? Well, it is, because you can see that the p-value for that thing is 0.00085, suggesting that the odds of seeing an observation that extreme or more, if you really have this null being true, is almost 0%. This would lead you to reject the null hypothesis and conclude that you have a significant test somewhere, right? This would lead you to conclude that you have a significant test, you have a significant variable base. So that's what he refers to here when he says, hey, is there a significant relationship between your rainfall and your experimental variables? So that you would say that, at this point, if you want to be very formal, and you should, because every time you talk about significance, you should do it within the context of the actual question. So you would essentially say you reject HO, and you conclude the alternative. And then that means that to conclude this means that there appears to be a significant relationship between, I should write this better, between, I'll write it here, between, latitude and rainfall. So, it appears that the higher you are, right, the more likely you are to experience rain. So you can see that because the positive relationship would mean that for higher altitudes, you're more likely to experience higher rainfall. Basically, that's what it's saying. Otherwise, if it was a negative relationship, it would mean that for lower values, you're more likely to experience higher rainfall. But it's actually positive, which means that as your altitude is increasing, your rain. So you really actually be formal. You should really actually say that. From filling this in, we really should actually say is the following. You should say, I'll write it here and then put it up, or I should say the answer. We reject the null hypothesis and conclude the alternative. There appears to be a significant association between latitude and rainfall. By the way, this is not enough. If I leave it here, this isn't really enough because you haven't actually really contextualized. What you really need to say is that as the latitude increases, the rainfall appears to increase as well. Right? That's really the direction of the effect. It's a positive one, right? That's really the complete conclusion. And I really should say, since P is less than 0.05, we reject the null hypothesis, right? That's what you really would say. That's a complete answer. Now, I did say that if you add another predictive variable, basically, you will see that the p-value you get for the grand model, the global p-value will not actually match the p-value for each of those predictive variables. You can see here that the global p-value is this thing here, which is still significant, but if you look at the actual p-value for each of those individual components, it is not the same. That's interesting. Now you might say, what happened here? Several things happened here. First of all, you can see that this is the global F statistic. What this tells you is it tells you that there are some, it tells you there's, when you have a significant p-value, but not all of the predictive variables themselves is significant necessarily. It would tell you that there is something in your model, that's significant, but it may not necessarily be all of them. So you would notice that there's something significant, but maybe not all of them. That's what this go. Then you need to actually go. You need to go to the individual F tests. So these are individual tests here, where just the global test. This will only tell. If you look over here, this will tell you there's some there. If you have a model that's significant, but it will not tell you which covariates is significant. To figure that out, you need to go over here. But I do want to point out that you can see that the global F is actually more significant than each of the individual p-values over here. This kind of, and moreover, you can see that Latitude's p-value went down when you added in these two things. These two things together tells you something happened in your model that's not necessarily very good. So I repeat this again for those who are watching later. There's two things to note here that's not right? First of all, you can see that the global F is actually more significant than each individual covariate, signifying that, and the second thing you can see that is that Latitude, which is perhaps the most predictive coefficient, because you can see from the scatter plot and you saw from the previous model how significant it was, the significance was shrunk when you add the other two covariates. This actually indicates you have a high correlation between your predictive variables. Whenever your predictive variables are too highly correlated, it does pose problems in your model basis. You can see that it doesn't necessarily always pay off to have too many predictive variables in the model. You can see that the effect of Latitude was shrunk because you added in covariates it's probably correlated with. For instance, Latitude is probably correlated with altitude, and it's probably even correlated with, and altitude itself is probably correlated with the front. Altitude is probably correlated from coast. Because they're all correlated in some sense, because they're all in some sense referring to geography or location, you have actually shrunk the effect of the most significant covariate when you added the other two. That is not a good thing. So you can see that you did this because your global F is more significant than each of the individual covariates. So whenever this happens in your model, it probably means that you need to remove something from your model. You cannot have them all there, right? So it means you have too many things in your model and you actually cannot include them all in there. This thing, and he may ask you this, that's not good. So you can see that. So how does your actual R squared here compare to the other one? Your R squared, you can see your R squared went up. The multiple R squared went up. The multiple R squared went up. So the R squared went up. This always happens. This always happens, even if your predictive variable itself is not significant. The R squared will always increase. When you add more explanatory variables. So it's not necessarily, this is why I said it. So what it's saying is that, what this means is that, actually I should say it's here, it is actually exactly 0.6003. What this means is that your model is more equipped in some sense to describe the trends in your data. Like the extent to which your model can actually accurately predict your response, your rainfall is increasing. But that doesn't necessarily mean it's a good thing. I said that it will increase. It's more equipped to deal with the trends of your data. Just because your model can actually predict your data very well doesn't mean it generalizes. When you include covariates that are in some sense when you include covariates that are not necessarily very good, while your model will overfit and accurately predict your data, it will not generalize beyond your data. So this is something to note. Overfitting is a real problem when you have too many predictive variables and they're not all equally significant and they're highly correlated to each other. It results in problems where even if your R squared went up, which should indicate your model is more likely to be able to predict rainfall in your data, it doesn't mean that it can generalize. When you take a different sample and you put that model in a different sample, it doesn't mean your model is good. So if your model cannot perform well in different samples of size n, it's probably not very good. Just because it's very good at predicting one sample doesn't mean it's actually a good model, right? So it's something to note. But here, so let's just keep this in mind, right? And this is actually going to be, I don't know if you've taken C67 yet, but when I say that it doesn't mean your model is very good, we always look to see how your global F is comparing to your actual individual F tests. Gives us a hint about multicollinearity sometimes. which isn't always a good thing to your model. In fact, it's almost never a good thing to your model. But anyways, what do you conclude about the importance of your variables that you did not include in your model? And did you not include in your model in E? So what it's really asking here is that, is there variables that you didn't include in your previous model that appear to be significant here? I mean, I guess you can say yes. It appears that altitude and from coast are significant. You did not include in the previous model. But I would say that, so I guess from an objective standpoint, p-value is less than 0.05. So p-value is p is less than 0.05 for from coast and altitude. But the problem is that so we might conclude they are significant. No, but on the other hand, we can see that the effect latitude shrunk. We may actually collinearity, multicollinearity. We need to check on our multicollinearity. That we need to check among our predictive variables. You know, before we actually, especially because when you look at the actual plots, for example, of from coast, and so with altitude and rainfall, it wasn't very good, right? It's not strong enough for us to feel confident that, right, the relationship is like that. Yeah, but yeah, just to be very clear here, you can see that almost the relationship is not that good, right? That is pretty problematic, right? Those probably insinuates that we have some collinearity in our model that in some sense is tricking us into believing our models, our covariates are more significant than they are. And this is something we probably need to address before we actually necessarily conclude our model, basically, right? So it's not, we have to be a bit careful here. So the take home really is that, like, all is not what you necessarily see. We probably need to be a little bit careful as it pertains to including those covariates in the model. So while they appear to be significant, I'm not entirely sure they are. So I suppose for this one here, so when it says make a suitable hypothesis test, the variables altitude and from coast significantly improve the prediction of rainfall. What do you conclude? Technically speaking, this is really a hypothesis test, right? So this means you're doing the same thing here, except you have you would call it beta 2, beta 3, beta 3. And based on the actual output, you will conclude that they're significant. So you'll do the same thing with this here, and you'll reject the null hypothesis, include the alternative at face value. This is because this is not the type of course where you ask why your model does or does not make sense, right? So, like I said, objectively speaking, you probably have some kind of collinearity, but it's not something we'll necessarily it's not something we'll necessarily delve into this course. So just based on the output, you probably will say that the p-value is significant for both of them, therefore similar, akin to latitude. They appear to improve prediction of rainfall over time. But if you go on to take C67, you probably realize there's a problem with the model. That you probably need to do some collinearity check, that you would probably find that at least for the most part, altitude does not actually predict rainfall, but it's highly correlated with, for instance, the from coast, because obviously I believe that from coast is probably I believe we can actually check. I have a feeling the from coast is positively correlated with altitude. And even if you look at from coast here, you might actually see that it appears to be a little bit negative. There's a negative association, right? So if there's any negative association between being on the coast and altitude, it might actually in some sense show up in the model. So it will appear like they're both significant when really one is not, basically. So I'll just have a look and see. Rain data. I'm just going to double check just to make sure that I don't give any incorrect information. So X equal, let's say, altitude. No, yeah. And let's say Y is equals to from coast. So if we just check and see geom point, and then we just know the following. So sorry, geom smooth. Let's say method equals LM. I just want to see what happens, and I'll just put SE equals false. I can see that there's a pretty strong relationship between those two things, right? You can see that it appears that if you're from the higher your altitude are, the higher your altitude, the more likely to be on the coast. The problem is that the correlation is pretty obvious between those two variables. So it may not, you can see that from coast may not be at all correlated with rainfall, but because altitude is a little bit correlated with rainfall, it will appear to be significant when in fact it's not true. If you remove altitude, it might actually improve the significance of the other two covariates. We can double check to see if, so this is what we call a confounder, right? So it's not that, for instance, that it's not that from coast is correlated with rainfall. It's just that it's confounding with its relationship with altitude. These are things to check because it's not good, right? So like I said, it does shrink the effect of your model. It does shrink the coefficients of your model. And you can see that latitude became less significant when it should not have, merely because of the influence basically of the covariate. So we just have a look and see. You can even see here, even with altitude and latitude, it's less significant. Really, the real problem is probably actually these two covariates here. There's a bigger relation between altitude and from coast, and that does actually influence the model, right? So we shouldn't include them both. One should probably be removed from the model, and that might actually improve the significance of latitude. So you can see that even though we'll conclude in some sense the p-value is significant for both altitude and from coast, it doesn't mean that we're complete. So for the purpose of example, you might say, hey, p-value is less than 0.05, therefore altitude and the from coast are positively correlated, but probably, both strongly are correlated with rainfall. And then you'll give a conclusion, or I guess because this one's actually negative, you might say there's a negative association between from coast and rainfall, whereas there's a positive one here, but that doesn't mean it's true, right? So you might say, but the p-value is less than 0.05, which means you conclude that as being from the coast, if you're unlikely to be from the coast, then rainfall increases because there's a negative association. So the less, for a decrease in being from the coast, you see an increase in rainfall, but that's not necessarily, so this is a conclusion you'll make based on the p-value, but based on common sense and looking at the way from coast is related to altitude, you might realize the problem before you make such a conclusion on your model, basically, right? So these are things to check, right? So you don't end up with a situation where you made a serious mistake with your model. This is probably more important in C67, where you might realize that that kind of thing can actually really erode your model a lot. But yeah, I will stop here for now. And if you have any questions, you can let me know. But I guess that's it. And this is entirely based on your assignment. So after the 10 a.m. tutorial, I will post this complete comprehensive RMD file, and I'll also post a YouTube video, and you can go back and rewatch things that you think might be important for your assignment. Otherwise, have a great morning, and thanks for hanging around, I guess. I'll stop the recording. Oh no, not stop. I want to pause the recording. Your assignment this week is on linear regression. I just want to see if he's posted it yet. He may or may not have. Let me see. Yeah, so he hasn't posted it yet, but he will, and you can see that it's going to become available tonight. It's based on linear regression this week, so this is why I took an example from his work. So it's called Rainfall. I just want to point out that if you open this, if you try to use read underscore, so this is actually just this is data that's available on his lectures or in his lectures. But the thing is, if you use read underscore table to open this data set, it won't work. This is because if you look at the data set that he's provided you, you'll see that there's more than one spacing here. So if you use read underscore table to open this, it will open in a very strange way, right? And I can actually show you guys that what happens when you use read underscore table 2 is actually a little less rigid. So it allows you to have more than one space, right? But read underscore table only allows you to have one delimiter. You can see that if you view your rain data, when you use read underscore table, it won't actually work. And this can actually, this is pretty problematic, right? So this is problematic for this is problematic, obviously, if you try to work with your data frame and it didn't open. Why doesn't it open? That's so weird. Oh, I just wanted to view. Oops, maybe me. I only had one coffee, so move it out of it. Okay, there you go. You can see that it's messed up, right? So because of the fact that there's more than one space between station and rainfalls, it kind of compressed these two. It compressed things like this. So you see, there's a bit of a problem based on the way the file looks. The spacing is messed up over here. And then you can see over here from CAS, it's supposed to be this thing here. It's supposed to go from CAS, because these are too compressed over here and doesn't match the spacing of the actual, it doesn't match the spacing of obviously of your variables. When you look at it with read underscore table, it's messed up, because read underscore table wants everything to be wants everything to be spaced equally with one delimiter. And it will not actually, it will load it in a very strange way. So read underscore table 2 is a neat way, because it's a bit less rigid to those kind of things. And so obviously you can see that when you open your data frame, it just looks better. Yeah, so read underscore table only allows you to have one space as a delimiter, right? So you don't have one space between your, so that means that it has to be the text file has to look like this, where there's a space between the columns and all of your entries are directly below your column, right? So it demands that you have all your variables are underneath your column and there's only one space between the different columns. But you can see that it's just, yeah, so read underscore delimiter and read underscore table, they're interchangeable in the situation where there's a space between your columns and all the variables are, all the numerical values are underneath your variable label. So read underscore table and read underscore delim are interchangeable when you have one space between. But the problem with your data frame here is that you can see that it's not true. There's a problem with, you see that these entries here are supposed to go into from cast, but it doesn't. And you can see the spacing is off by a factor of, like, it should be shifted 1 to the left for this one. It should be shifted a little bit too. And you can see that, yeah, there's a bit of, all the values are compressed in here. And it's not spaced appropriately for the actual variable. So for instance, altitude is spaced fine, but then rainfall should actually be over here. This should be moved 1 to the left from coast. So as a consequence, you try to open up the CSV file, or the text file, because it's not actually presented in a way where there's a space between each of the different columns and all the entries underneath their actual underneath their variable label, it doesn't open appropriately. Read underscore table 2 is a bit more flexible. It kind of can make sense of inconsistencies and where your actual values are positioned relative to the variables, and that's why I was able to read the text file as it was, whereas read underscore table was not able to do it. Right, this is something to know. Okay, so it says make a box plot of rainfall figures and explain why the values are reasonable. There's a note Ken made here where he says that actually it cannot be the case if rainfall is negative. So please check yourselves. Like, if you have a variable like time or distance and you see negative values, that's not right, right? So you have to remove those things if it appeared in your assignment or something, because it's very unusual, right? So it's even more unusual than having very large values of rainfall, because it truly does not make sense for you to have right, negative rainfall. The most it can be is 0. The lowest it can be is 0 is if you had no rain, basically, right? So you couldn't see any unusual values can be seen in your box plot. So you do have a couple of unusual values where you have this value of rainfall. It's like over 7, it's around 75. That's kind of unusual, I suppose, right? But and then it's a bit far from even the other outliers, which are kind of over here, right? So you have one sort of strange rainfall, but it's not too unusual. You just had a day where it rained quite a bit, basically. Anyways, we can obviously make a point. We can ask ourselves, is it really appropriate to use linear regression here? If we're going to do it, we should really ask ourselves if the method's appropriate, because you can see that linear regression is something you use when your distribution for your response variable is normal. So what we're really assuming here is that whatever rainfall happens to be, I'm actually going to leave this. We're assuming that rainfall is actually, normal with a certain, I guess, mean and a certain variance, right? So you can see that this is actually a conditional mean, because you can see that if we can express like the following: y is equal to beta naught plus beta 1 xi plus epsilon I, and this is the error that's distributed normal, and that's why you actually have this error term here that is sigma squared, because this part is fixed. This is the part we're going to estimate and using the linear model. It's the fixed part of the model. The error we can't really control, but we hope that it's kind of small, obviously. But you can see it's a conditional thing. It's a conditional mean, right? So this means that we hit the expected value of your yi. So it's actually this. It's actually conditional expected value of yi given xi is equal to beta naught plus beta 1 xi. Does anyone know why it's this? And you drop the error term. How come you can drop the error term? Anyone see why we can drop the error term here? The mean is 0, basically. And yes, if your error terms are not normal, you cannot use LM, basically, right? So, and yes, so the mean is 0. So that's why, as Jimmy is saying, the mean is 0. That's why, because when I take the expected value of this thing, really what you have is the expected value of epsilon I, which is 0. Now, yes, the answer to the question is if you truly don't have a normal distribution to your error terms, you cannot actually use the LM model, because you can see that if this part is fixed, the part that I highlighted is fixed, if this part is fixed here, what this means that the actual distribution is coming from the error terms itself, because this part is fixed. There is no distribution there, but this part is normal. The distribution is coming from the error terms itself. And what you actually really have is that for every unit increase in, let's say, xi, if you have some kind of linear relationship, let's say it's positive, let's suppose your x is increasing like this, and you have a distribution on y that looks like this, right? So maybe you have another value of x that increase. You have a distribution that is normal, right? So it's a conditional distribution where the mean value happens to be where the dot happens to sit in the middle. So it kind of looks like this, right? So you're supposed to draw a line of best fit to that thing. So you really have a distribution that is normal. And really, because your yi is normal, you have a range of possible values your yi can take for a given x, and it's a distribution on that thing. Where the dot you see is what you truly observed, but you recognize that if you take a different sample of size n, you'll get any value on this distribution here that is normal. You can get any value on the distribution that is normal when you take a mean, when you take a normal sample, right, and you have error terms that are distributed normal. Now, if your distribution is not actually normal, this line of best fit doesn't make sense, right? So this is why we actually check the shape of the distribution. You have to check the shape of your distribution, basically, right? You have to check the shape of your distribution, basically, right? And how do you do that? You need to look at the box. You can do two things. Either look at the box plot like he's asked you to do here first, or you can look at the histogram. But you can see that from the box plot, it looks kind of centered. If you just disregard the outliers, at least this part here looks somewhat normal. The problem we have is that we have a couple of upper outliers that before we actually placed a linear model on it, you probably have to address, or we're not going to do it in this lecture, but in theory, if you wanted to put an LM model on this data, you probably would need to address the upper outliers because it might actually be a bit strange. to assume normality when you have heavy skew in some sense, right? But anyways, so the first thing, I'm going to plot the rainfall again on all the variables basically, right? I'm going to plot the, I'm going to plot the rainfall, and you're going to see, you're going to see not all predictive variables are equally good. So if I just show you the data set again, you'll see that you actually have 3 quantitative predictive variables. These are these ones here. I'm not going to use this one here because this is actually a discrete thing. You can see that this is categorical, right? So while you can put categorical variables into the LM model, that's certainly something that's permissible. I'm not going to do it in this just yet because we cannot look at scatter plots when you have categorical variables. It doesn't work out like that, right? So anyways, I'm going to plot these things. So first of all, I want to say that if you look at last week's tutorial, you'll see that when I wanted to put 2 things in the same panel, I think it was like mortality for people who are 30, who are both male and female, you notice that I used facet wrap and I used the STACs to put them on the same panel. This doesn't work here because obviously I don't have any categorical variable to put them on put a facet wrap on. So in order to put them on the same panel, what I actually did was I installed Grid Extra. That's the thing I'm going to use to put them on the same panel. So how can I do this? I'm going to plot each of those things separately, and then I'm going to put them in a grid arrange. Notice that if I change the number of rows to 2, instead of having it look like this, it will transpose it basically, right? So I will transpose it to look something like, oops, like this instead. But I don't necessarily like the way it's up to you. I prefer it the other way, but it's up to you. If you want to have them on the row or column space, you just change it, right? So anyways, I like to look at it like this, but like I said, it's up to you to display it how you like. If you put a number of rows equals 2, you can imagine it will transpose your graph. Anyways, you can see that they're not equally significant, or so I should say they're not equally predictive. We can certainly see that as latitude increases, the amount of rainfall you get increases too in a positive direction. But when we put a line of best fit through altitude and rainfall, it looks tentative at best. It's almost looking like we're forcing a line of best fit, because you can see that none of the points actually sit on the line, right? You can see that the line of best fit is kind of like over here, but then the points are either really low or really high, so they haven't really actually necessarily captured the line of best. The line of best fit hasn't captured the observed value. So when you put this into an LM model, you might imagine that maybe one would be more significant than the other, right? So so here it says, look at the relationship of each of the variables with rainfall, justify the assertion that latitude seems to be the most strongly correlated with rainfall. Is the relationship positive or negative? So I'm going to give you I'm going to tell you how to explain this in a way that looks good. Okay, so answer. So first of all, I'm going to plot I'm going to plot from coast. So you can see that from coast is actually the first variable where it's actually a negative correlation. But actually, you can see that for to answer this, the best variable is actually latitude. So I'm going to say here that I'm going to say the following answer. The relationship with latitude and rainfall is positive, as the values as the latitude increases, the amount of rainfall increases. And I'll make a note here that it is the strongest relationship because we can see the strongest slope of the line, and the fitted line does a good job of predicting the observed values.
you can actually see that it sort of maps out the observed values. Whereas the other ones, you can see it's lukewarm at best, that there's a lot of scatter around the line, the other two, so we probably wouldn't know them as the better ones, right? So that's probably how I would answer the question. Please be explicit when you're answering, right? So try to put as much detail as possible, so there's no mistake what you think you're thinking, or what we think you're thinking. Yeah. Cool. I'm going to fit the line of best. So I want to point out that if you look online to fit a line of, so first of all, you should be using LM. But the thing is that LM is a thing in CRAN that only really works for linear models. You cannot use this for, if you go on to take C67 or something, you cannot use this for logistic or any kind of generalized linear model. There is something called GLM, right? So if you do something like GLM, you do something like, you know, family equals Gaussian, you will actually get this. So I'm just going to point out this thing here. You'll get the same line. So I'm just going to show you. Oops. GLM. You'll get the same line because the GLM is a generalization of the linear model where your link does not have to be linear. So Eddie asked, if your error term is not normal, does that mean you can't use linear regression? I said yes. If your error terms are like logistic or anything else, you would use a GLM instead of LM, and your family, the family you would use would be something else, be it binomial, multinomial, gamma, whatever it happens to be. It just wouldn't be normal, or sorry, it wouldn't be Gaussian. Gaussian is the family of the class of family that defaults to a linear model basis. This is why the output you got for this GLM is the same output you got when you just run the LM, because it's the same thing, right? Anyways, you can see that there's a couple of things he wants you to note. He says that please pick out the slope, the intercept, and the R-squared. When you put your thing into the model, how do you actually do this? It is rainfall as a function of latitude, right? So it's rainfall given latitude. Please be mindful of X and Y. If you mix up the order, you will get a different estimated line of best fit. You might be confused as to what Y and X happens to be. X is the thing that is least likely to be messed up by measurement error. So let me repeat again. X is the variable that is the least likely to be messed up by measurement error. You can imagine that it's pretty hard to mess up latitude. It is a geography. It either is or it is not, but it's pretty easy to mess up rainfall, like how much rainfall you had in a given day is variable and subject to a lot of things you can't control. But latitude is a geography on a map, basically. It's a fixed thing, right? That can vary according to your measurement very minutely, but not too much. Whereas rainfall can be varied by a lot of factors. So you would never think that latitude is a function of rainfall would be a thing. You'd think that rainfall could be determined by a latitude. And so when you put this into the model, it's actually Y given X. So this specific thing is saying Y given X. If you don't want to, if you want to just plot the intercept model, it would just be this. If you just put rainfall given 1, you're only fitting the actual intercept model. You have not fitted any kind of slope of the line, right? So I'm going to go back to latitude. Anyways, there's actually 2 estimates for R-squared. Please be mindful of which one you're choosing, right? So you're not interested in both of them in this course, right? So the one you're interested in is multiple R-squared, not the adjusted R-squared, because the adjusted R-squared is something you use when you have variation in your, what do you call it? In your, when you have variation in your, sorry, the adjusted R-squared is something you use when you want to do, what do you call it? Model selection, right? Like when you want to drop covariates, you think you have too many covariates in your model, you might use the adjusted R-squared, but otherwise the multiple R-squared is a thing that tells you how your response variable in your model is changing as a function of the covariates you included, basically, right? So you can see that your R-squared is actually what you see here. It is 0.3326. Now, what does that mean? So let's just point out that the R-squared here is, so I'm going to point out a couple of things. So I'll just say 1, the R-squared is 0.3326. 0.326. That means so that anyone else is watching later on doesn't say it's 0.3088. Does anyone know what this means? So first of all, this is called the coefficient determination. So what is this telling you? It tells you the proportion of the variation in your rainfall that is determined by latitude. So you see that it's telling you how much you can control by your latitude variable. But I want to point out something here. It's actually the case that r squared is equal to little r squared. I guess I could put this in math mode. It turns out that r squared is actually equal to a little r squared. Does anyone know what little r squared happens to be? What is that? You know what little r squared is? What is little r squared? Anyone have any guesses as to what little r squared is? It's the correlation coefficient, yeah. So, I'm going to make this note where little r is the correlation coefficient. This is not a trivial thing. Why? It's not a trivial thing because when your r squared, when your little r is low, it's telling you that your coefficient determination is going to be low. What does that actually mean? It means that to some extent, the correlation you have between x and y precedes how strongly you can predict your proportion of rainfall from your latitude. So the correlation between your latitude and rainfall kind of in some sense precedes how strongly you can predict the variation you see in your rainfall from latitude. In the sense that the correlation between those two things is very poor, your ability to predict rainfall is going to be very poor, basically, right? So this means that if the correlation between latitude and rainfall is poor, then the ability to predict rainfall from latitude will be poor, basically. Now, that's what I wanted to point out. But the thing I also want you to note is that this, in some sense, intuitively tells you you can actually intuitively find out what your little r squared happens to be, because you know that a big R squared is equal to little r squared. This insinuates that you can actually figure out what r squared happens to be. Here, notice that little r is equal to the square root of this, which is equal to, we can see. I really have to do this. I'm sorry, I really have to do this. Yeah. Oh my goodness. There you go. Okay. So first of all, I want to point out that generally speaking, when you hit the square root of something, you guys know that this means that you actually have two roots. However, what is the correlation? Is it negative 0.568? Or sorry, is it negative 0.56 or is it positive 0.56? Anyone know what it is? What do you guys think? Is it positive or negative one? It is positive. How come? I agree, it's positive. How come it's positive? Yeah, that's a good thing. So thank you for pointing that out, Eddie. The sign of your slope is positive, guys. Now, I don't know how many of you have taken C67 yet, but that's okay if you haven't. However, since the sign of the slope is positive, it turns out that your slope is a function. Yeah, your slope, no, it's true in general. Yeah, yeah, that's true. That's true, Eddie. But actually, to be clear, if you want to figure out what R squared happens to be, I'll point out the formula for R squared in a second, and you can determine if you think it's true or not. To be fair, there's a correlation between your slope term and your your slope term is a function of your correlation. So technically speaking, your actual slope term is the following. So your slope beta 1 hat is actually R times S of Y over S of X. So you can see that that's the formula for your slope term, which means that if your actual slope term, if your correlation is itself positive, your slope term has to be positive. On the other hand, if your correlation is negative, your slope term has to also be negative, because these two will always be positive. Your standard deviation can never be negative, which means the sign of your slope term is entirely determined by the sign of your correlation. So because the slope term in our summary statistics is actually positive, that forces the correlation to actually be positive too. But to answer Eddie's question, he was saying, is it true that if you have one predictive variable that you can only make a conclusion that R squared is equal to R squared? The answer is no. It's actually like that. You can actually prove that in general. Actually, you can prove it. I guess, let's see, because there's actually a way, there's a way to mathematically prove, and I've actually asked my students this before. I've asked my students to mathematically prove using the formula of this in the proper form, because you know it's actually equal to the sum of like xi minus x bar, yi minus y bar divided by, it's this, right? So I've actually asked them to use this formula here to prove that this is true. But actually, let's express this. R squared is equal to SS regression over the SS total, right? That's what that is. So this doesn't mean that if your R squared, so if you have more than one predictive variable, can you actually express this as this? You cannot say this if you have more than one predictive. If you have more than one predictive variable, you cannot really say R squared is equal to R squared for one covariate, because you would have like more than one covariate. So this is really a short form, I suppose, for one predictive variable. In general, it's actually this. But you can actually show, Eddie, that these two things are equivalent when you have one predictive variable, basically. But it's not true when you have obviously more than one. But you're right. It doesn't make sense to say R squared, right, when you have more than one. But you can show that these two things are equivalent when you have more than one. So when you have one exactly. Otherwise, this formula is really the general formula where this is the total variation. This is actually, to be clear, it's actually equal to the following. It's actually equal to the variation you see in Y. This is equal to the variance of Y squared, so divided by this thing here. So this is actually this. This is a bit more than you need to know, but I'll just say it's actually this. It's actually this. You can see that it's actually a ratio of the variance you have in X and Y times the slope term. Where if the slope term is actually 0, you have this R squared will be 0, saying that your actual predictive variables are useless, right? Otherwise, if your predictive variable is not useless, well, then you will actually see this can be at most 1 when your predictive variable is 100% predictive, right? So this is actually a general formula, right? And you can actually see their equivalent. In the case of one predictive variable, it's actually pretty equivalent. If you have more than one, this is not the formula, but this is the formula for one predictive variable. For one predictive variable, this is the formula, which is actually equivalent to saying this. And you can see that when this is truly 0, you have R squared 0. But anyways, it's probably more than you need to know, but I will say this is the formula for one predictive variable. And so you can see that Eddie's question is it true that this is true for more than one predictive variable? It's not true for more than one. In fact, this is the general formula when you have more than one. And in fact, I'm going to show you that in this tutorial here. We're going to see that the R squared you get when you add more than one predictive variable in this tutorial is not going to be based on just one predictive variable, one covariate. So you cannot say that, right, that this is true. Anyways, what is the actual slope term? Well, the slope term, we have this thing here, as we said. You have this thing here, right? Which is equal to, I think it's -113.0 3028 plus 3.59, I think, is it? Yeah, 50. And I guess just say latitude here, right? So it's really actually latitude. So whatever unit increase you have in latitude will be associated with the mean increase in your actual rainfall by a factor of this, basically, right? So what this model actually says is that when you increase the latitude by 1 unit, I guess the unit being 1 degree, you'll see an increase in the average rainfall by a factor of 3.5950, right? So it's a positive one because as Jimmy said, you can see that the slope term is positive. So this relationship is overall positive where they're going to increase together. This is also seen in the scatter plot too, right? They're all going in the same direction. Yeah. So I gave you the R-squared, I gave you the actual I gave you the slope and intercept. The only thing I didn't give you is how to make sense of significance. Well, first of all, this is a hypothesis test. To set up the test, well, you really want to show that latitude is significantly correlated with rainfall. So your hypothesis is always against the null distribution, where you might assume that there is no relationship. No relationship indicates that the slope term is 0, basically, right? So on the null distribution, you're trying to see how far your test statistic is from 0. Why is that? Because generally speaking, T is equal to beta 1 hat minus beta 1 over S of beta 1 hat. But you hypothesized in the null, you have no relationship. What you're looking to see is the ratio of your actual, your estimate divided by the standard error. And in this example here, does anyone see what this is in the output? What is your T statistic from your output here for this test in R? What is a T statistic? Anyone see what it is? So the T statistic here is actually, the T statistic here is actually, oh, someone's answering. Yeah, for latitude, because that's the only slope term you have here. Yeah, it is. So it is 3.736, right? So this is actually 3.736. And actually, I just want to point out, you can actually compute this without seeing it, because you can see that your actual estimate is 3.595. So if you divide this by 0.9623, you'll actually get this thing here. Right, so if you divide these two things together, you will get this, because like I said, the formula is actually this. So if you divide, the formula is this, it's your beta 1 hat divided by S of beta 1. So if you divide them into each other, you'll get 3.736, which is actually over here, right? And the question is, how far is 3.736 from 0? Like if the null is true, you should see your evidence kind of close to the center over here, right? It should be somewhere over here. Now the question is your actual test statistic close to, right, 0, or is it not? Well, the p-value for your actual test statistic is like 0.00085, so 0.00085, which is certainly less than 0.05. This is actually a reject the null hypothesis and conclude the alternative. So what you're going to conclude then is that there appears to be a significant association between latitude and rainfall. Now, this is not quite enough, right? You should really actually talk about the direction of the effect. I think I actually put a note here where I said that there appears to be a significant association. I said that I went further and I said that as the latitude increases, this is really actually a positive one, as Eddie pointed out, the rainfall appears to increase as well. So we should really be explicit here and say that how we think this relationship is being governed is governed by something that's positive, whereas one is increasing, then of course the other one's increasing too. We can see that, right? So that's something we're kind of looking to explicitly kind of state. Okay, the last thing is, so here it says fit a multiple linear regression, basically. So this is getting to the question that Eddie asked. Actually, I think it was actually Jimmy that might have said something about anyways, the question that Eddie asked about, is it true that the big R squared is equal to little r squared only in the situation when you have one linear regression, when you have one predictive variable? And I kind of said, yeah, it doesn't make sense to talk about like that when you have more than one. And you can see here that I've actually included all of the predictive variables, right? So you can actually see that you get a couple of things here. You get a global, you get a global p-value. Notice the global p-value, guys, is actually less than the p-value you get for each individual predictive variable. That's actually a problem, right? So that's actually a problem, because you can see that the p-value for the global test, it tells you what? It tells you have at least one significant predictive variable. It does not tell you where that significance may be. It will tell you have one significant predictive variable. It won't say where it is, basically, right? So you have one significant predictive variable. It will not tell you where it happens to be. That is something that you have to figure out, basically, right? Yeah. So this means that you have to figure out, you have to figure out where it happens to be, because it will not tell you. Right? Okay. So what does this mean? Well, you can see that when you look at each of the individual p-values, will tell you they're all significant. However, and that's fine. It will tell you they're all significant, but you can actually see that each of the p-values for these coefficients are actually less significant than the global p-value. Usually that happens when you have multilinearity, in the sense that like the significance of your covariance actually shrunk when you included too many predictive variables, basically, right? So because you included too many predictive variables, in some sense, the significance of your coefficients kind of got messed up a bit, right? That's why you can see that while your global F is actually bigger than your actual individual Fs, that usually happens when you have too many predictive variables that are correlated to each other, and that you have confounding in some sense, right? So if you're going to be asked about which ones is significant, you would say they're all significant because they're all less than 0.05, but probably would need to do a little bit of work here, because we're a bit suspicious about the fact that they're all pretty highly correlated. This is something we should probably know, right? Yeah. So here it says, what is the R squared for your regression of this particular model? You can actually see the R squared increased. I want to make a note here and say that the R squared, guys, will always, and so just to answer the question about, is it true that R squared is equal to, big R squared is equal to little R squared? No. Not when you have more than one predictive variable, because you can actually see here that your p-value and your actual F test is based on the global F, is based on all of the predictive variables. So you cannot actually say that you can no longer say that multiple R squared is based on one predictive variable. So it's no longer a little R squared. You can see that it's based on 3 of them. But I want to point out that your big R squared will always increase when you keep adding more predictive variables. Notice it went from 0.3326 to 0.6003. What this is saying is that when you add more predictive variables, the ability to actually mimic or actually predict what's going on in your data increases. Well, we will always get a better ability to predict our data when we add more covariance. But the problem is that we don't want to actually just predict our data. We want to predict beyond our data, right? So it is not, because remember, guys, the data is only one sample. Ideally, you take multiple samples of size n, and each of these different samples will yield a different test statistic. What you really want is that, on average, those different test statistics are kind of consistent and kind of converge in the same values. But what you don't want to happen is a situation where for one data set you picked out, your model only does a good job at that data set. And when you take that same model and put on an independent data set, it does very poorly as a model, right? So your R squared will always go up when you add more predictive variables. That is not the test you use to determine if your model is good, right? You can see that it will always go up when you add predictive variables. It doesn't necessarily mean your model is good. So obviously it's bigger
we might say the extent to which your R squared actually is able to capture your data or the trends in your data increases, but that is not the goal basically. We obviously want to generalize beyond our data, right? So this is something to think about, I guess, beyond the scope of this course, because obviously you would go on and check collinearity. The question you get here says, what do you conclude about this, the importance of the variables that you do not include in E? There's two ways you can argue this, and I guess in an assignment you wouldn't, it depends on how well you argue each standpoint, right? If you take the objective route and you look at the p-values, you will then say that, well, for both altitude and forecast, the p-value is less than 0.05. So you'll reject the null hypothesis and conclude they both appear to be significant. Fine, right? But then you could also argue, on the other hand, that you probably have some kind of collinearity effect and it shrunk the significance of your latitude. How do we know this? We know this because the global F is actually more significant than the F test for the latitude variable, which is off basically, right? But if you make either conclusion, you argue it very well, I would accept either answer. I personally probably wouldn't include them all in the model. And I would do some more work where I actually look to see the correlation between the variables. So here I'm making an actual GG plot of, I'm making an altitude versus forecast, because I suspect that altitude is kind of related to forecast, is related to from coast, like where you are on the coast might be in some sense related to your altitude, right? So perhaps if you're further along the coast, you might be at higher altitudes, and I suspect that the relationship is going to be significant in some sense. So if I run this, I can actually see that there appears to be some kind of positive relationship between altitude and from coast. That's pretty problematic because they were both included as predictive variables in your model, which might actually cause a confounding problem where it's not that from coast is significant in predicting rainfall. So from coast may not be significant in predicting rainfall, but what it might actually be is highly correlated to, it's maybe highly correlated to, what do you call it? To the altitude. And that's what you're seeing in the model. So we have to be a bit careful here, right? It could be the case that, it could be the case that the from coast is related to altitude and is not necessarily itself highly correlated to rainfall. And when you include them both, it looks a bit, it kind of in some sense diminishes the effect of altitude or rainfall. Sorry, it diminishes the effect of altitude against rainfall and altitude against latitude. So you may want to remove from the model. So I would accept any answer where you kind of said, okay, so there appears to be a correlation between predictive variables, and that in some sense diminishes the model because you can see that the global F is more significant than each individual test for the coefficients, which shouldn't happen basically. Or I would also accept that your p-value is significant. Is significant for both those coefficients because it's an applied course. So if you haven't seen the advanced topics, you may not know about multicollinearity. So I would also accept where you did a formal hypothesis test, and just if you did a formal hypothesis test akin to what we did with latitude and conclude that it was significant, using something like this with the two covariates. Where you're doing something like, what's that? Something like the following here, like these two things, I would also accept that as well, as long as you make sense of your argument. Right, so. Any questions about this? So I will post the thing as soon as I can. Yeah, I'll post as soon as I can, which is hopefully soon. Yeah. No worries. Thanks for attending. I will post this today because obviously your assignment is going to come up pretty soon. So you might want to have a look and review stuff before your tutorial, before your assignment comes up, which is today, actually comes up today. So have a great day, everyone. I'm going to stop recording.